Hello future engineers, welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe, press the notification bell, and if you find my videos helpful, not only to you but to your friends, then share them so that I would also be encouraged to do more lecture videos which will be beneficial to your studies. So I hope that you will enjoy watching my videos and you'll learn a lot. So this is the first problem on the topic strain. So the following data were obtained during a tension test of an aluminum alloy. The initial diameter of the test specimen was 12.827 mm and the gauge length was 50.8 mm. So we have here the loads and the elongation. So plot the stress strain diagram and determine the following mechanical properties: the proportional limit, the modulus of elasticity, the yield stress at 0.2% offset, and ultimate stress, and letter E, the nominal rupture stress. So before I proceed, I do not claim any originality of the problems I presented herein. All these problems are either revised by me or from converted from USCS units to SI units, and all the problems, most of the problems are taken from the book by Pitel and Qsalaas of their book Mechanics of Materials, second edition. So I hope that I am clear here about the source of these problems. Okay, so first let's have to compute the stress, which is force over area. So of course 0 divided by area, so it's also 0. Then 10,280 divided by pi over 4 times 12.827 square, it will give us 79.55 megapascals. So these are in megapascals. Then 2645 divided by pi over 4, 12.827 square, it will give us 159.8 megapascals. All these are tension because the test is tension, but also applicable for compression if the test is for compression. Then 30,920 divided by area, which is pi over 4, 12.827 square, 239.3 square, then 41,335 divided by the same value, so 319.9, 51,610 newtons divided by same area, 399.4, 57,840 divided by same area, so 447.6, 62290 divided by same area, so 482 megapascals, then 64,070 divided by same area, 495.8, 64515 divided by area, 499.3, 64960 divided by same area is 502.7 megapascal, 65850 divided by pi over 4, 12.827 square, 509.6, 64,960 divided by area, it will give us 502.7 megapascals, and rupture strength is 60,510 divided by original area, so 468.3 megapascals. Then for the strain, which is elongation, uh, or strain is, let's solve for the elongation first from stress length over E. And modulus of elasticity E here is, of course, 200 gigapascals. But the strain is simply elongation because these are elongation divided by the gauge length, which is 50.8. So 0 divided by 50.8 would also be 0. So next, 0.056 divided by 50.8, it gives us a value of 0.011. So we have to plot horizontally 0.011. 0.011 would be somewhere here, and vertically 79.55. So that's almost 80. So that's the point. Next is 0.112 divided by 50.8. That's 0.022. So somewhere there, then the stress is 159.8, almost 160 megapascals there. Then 0.168 divided by 50.8 is 0.033. Then 239.3. 239.3 is almost 240 there. Then 0.224 divided by 50.8 is 0.0044. So the partner is 319.9, almost 320. Next is 0.279 divided by 50.8 is 0.055. This is 0.005. So 0.0055 is very slightly close to this vertical line here. And the stress is almost 400 megapascals. So it's approximately there. Then 0.381 divided by 50.8 is 0.0075. So that's between these two. So 0.0075, and the stress is 447.6. So it's somewhere there. Then 0.508 divided by 50.8 is 0.01. So it lies on this graduation here. And the stress is 482, so slightly above 480. Then 0.65 divided by 50.8 is 0.0125. Because this is 0.015, 0.0125 would be between these two vertical lines. And the stress is 495.8, so it's somewhere there. 1.524 divided 50.8 is 0.03, so it is exactly on this line here. And the stress is 499, so it's slightly above 480. Then 2.032 divided 50.8 is 0.04, so it's here. And the stress is 502.7, so you just approximate it. Then 2.54 divided by 50.8 is 0.05. Then plot 509.6, 0.05, so it's here. And 509.6 is slightly above that. Then 3.048 divided by 50.8 is 0.06, so it's here. And the stress is 502, so it drops a little. Then lastly, we have 468.3, but we do not know the elongation for that case, because at that test, the steel specimen fails or it fractures. So we see that in this plotting, it is straight, almost straight up to this value here. And this is about this value here, 399.4. Then the displacement is 0.0055. So from there, the proportional limit is equal to the maximum value in the straight line portion. So it is equal to 399.4. So that would be our answer for part A. Let's first draw the curve. And that represents the stress strain diagram. So for part A, the proportional limit is 399.4 megapascals. Then for letter B, modulus of elasticity. Since stress is proportional to strain within the proportional limit, then this stress 399.4 is equated to modulus of elasticity E times the strain, which is 0.0055 for that case. So stress proportional to strain, so 399.4 equals E times 0.0055. Therefore, modulus of elasticity is 399.4 megapascals divided by 0.0055. That would be 72,628 megapascals. Then usually modulus of elasticity is in gigapascals, dividing farther by 1000, so we have 72.628 gigapascals as modulus of elasticity. Then for letter C, the yield stress at 0.2%, so 0.2% is 0.002, so that's about 0.002. Then from there we draw line parallel to this straight line or tangent. Then it intersects this curve, stress strain curve, and that is the approximate yield stress. Then if we estimate that, that's around 475 megapascals. So our estimate for yield stress is 475 megapascals at 0.2% offset. So that's the definition. Then letter D, ultimate stress. The ultimate stress is the highest stress or the highest ordinate in the stress strain curve, and the highest is this point here at strain of 0.05, and this is the highest value. Therefore, the ultimate stress or ultimate strength is 509.6 megapascals. Then finally, the nominal rupture stress is equal to stress at nominal area or original area. So it is equal to 468.3 megapascals. So that's it for this problem, and I hope that you were able to follow. So let's proceed to our second problem on strain. A uniform bar of length L, cross-sectional area A, and mass density rho is suspended vertically from one end. Show that the elongation of the bar is given by rho g L square over 2e, where g is the gravitational acceleration and e is the modulus of elasticity. Then part B, if the mass of the bar is m, show that the elongation would be mgl over 2ae. So let's draw the figure so that we can analyze it well. This is the bar, suspended bar of length L, and cross-sectional area constant. But if we section the bar, we notice that the tensile force will depend on the distance from the end of the bar. So in general, if we consider a section Y distant from the bottom end, then the tensile force there would be equal to the weight of this bar of length Y. And therefore, the force is also equal to that Wy. But the length is not constant. But if we consider a differential length dy, below the section is Wy, and above the section is also P, which is equal to Wy. So take note that area is constant for that case. So since we only consider length of the bar equal to differential of y, and we are forced to do that so that the stress on this section at the bottom and on the top would be the same or uniform, because that's only dy. So let's do that, and let's begin with the differential deflection formula. Originally PL over AE, it will now be equal to P differential y over AE. AE is constant for this situation. So P is Wy, and it is equal to density times G times volume of the wire below this section. So the volume is equal to cross-sectional area times the length, which is y. So differential of deflection is equal to P dy, because the length is dy, so that the stress below this section and above the section will be uniform, so that we can apply this formula. Therefore, the deflection is the integral of P dy over AE. And that is from PL over AE. In this case, if we consider the entire length, then the stress distribution would not be uniform. For it to be applicable, then we should only consider length of dy, so that the stress below and above that section would be the same or uniform. So substituting into this equation here, where P is rho g ay, and AE is the same AE because it is constant. And canceling out A, then integrating, so delta equals rho g over E, then integral of y dy from 0 to L. So integral of y dy is, of course, y squared over 2. We limit 0 to L, so rho g over E, y squared over 2, 0 to L. So finally, the deflection would be rho g L squared over 2E as uh, stated in this problem. So that's the deflection, and it is true. Then for part B, if the mass of the bar is m, show that the deflection is mgl over 2ae. So if we multiply this formula here by a over a, which is 1, because mass is density times volume, so it is density times the volume of the entire wire. Suspended wire is cross-sectional area times length, and there's no area in this formula. So if we multiply the numerator and the denominator by a, then we can write rho AL here. Let's break L square into L times L. So rho AL times GL over 2AE. And take note that rho AL is the mass. So substituting, deflection equals mgl over 2AE, which is equal to that expression. So that's it for this problem. For the next problem 3, the steel strip has a uniform thickness of 50 mm. Compute the elongation of the strip caused by the 500 kilonewton axial force. The modulus of elasticity of steel is 200 gigapascals. So here is the given figure. So notice that there are two segments, and each segment is identical with the other segment. So therefore, we only compute the deflection of one segment and multiply it by 2. That will be the total elongation of this strip here. And the thickness of the strip is 50 mm perpendicular to this screen, and it is constant. So because the cross-sectional area varies with distance from the left end or from the right end, then we have to consider the formula, differential deflection. So let's make the cross-sectional area constant so that the stress will be uniform for that case. So we will have to consider at section X from this left end here, so that the cross-sectional area left and right would be the same. So at the left, because the differential distance X is very, very small, so we can say that the area is now uniform and the stress would also be uniform. The force is constant at 50 kilonewton, 500 kilonewton force. So by similar triangles, we draw this line here parallel to this bottom side, so that this is 120 minus 50, so this is 70 mm, and the entire height of this strip is y, and therefore for the application of the similar triangle, this triangle here, this is y minus 50. So that's 70 mm, and this part is y minus 50. So by similar triangle, this is the formula. Differential deflection is force P, which is constant. The length should be dx, so that the stress just to the left and just to the right would be the same, over area at section X, which is changing, times E. But at this section here, the area is equal to area X. So y minus 50 as to X equals 70 as to 1000. Therefore, y is 0.07x plus 50. So that's the expression for y. Substitute it here. So ax, by the way, is 50 mm, the thickness perpendicular to the board, times height y, 0.07x plus 50. So substitute into this formula. Differential deflection equals 2 times quantity force, which is 500,000 newtons. Let's convert 500 kilonewtons to newtons, to make the deflection dx over area in square. This is in square, 50 times 0.07x plus 50. Then E is 200,000 megapascals or 200,000 Newton per square to make the unit square. So differential deflection equals 0.1 dx over 0.07x plus 50. So we can evaluate this by ln. So deflection is 0.1 over 0.07. Integral from 0 to length is 1000. So times 0.07 dx over 0.07x plus 50. So that if the denominator issue, the differential of the denominator is this numerator here. That's why we introduce 0.07. By the way, the deflection is multiplied by 2 because there are two segments, identical segments. So evaluating the integral, it is 10 over 7 ln of 0.07x plus 50, limits from 0 to 1000. So substitute, it is equal to 1.251 mm. And that's the deflection in this problem here. Okay, let's proceed to problem 4. The compound bar containing steel, bronze, and aluminum segments carries the axial loads shown in the figure. The properties of the segments are the working stresses, and the working stresses are listed in this table here. So the question, determine the maximum allowable value of P if the change in length of the entire bar is limited to 1 mm and the allowable stresses are not to be exceeded. So what is the actual elongation of the bars? So there are two criteria of investigation. In this case, one is based on strength of the materials and the other one is based on the allowable deflection, which is either elongation or contraction. So before we proceed, we have to draw the axial force diagram. So if we cut a section in this aluminum segment, then we have a force 2P, so the stress should be to the left, so it should be in tension. So this is the axial force diagram. So for aluminum bar, beginning with aluminum bar, it is tension 2P, the load is 2P. Then if we section this bronze here, so we have 2P, then this is 4P. The net load is 4P to the left. So the reaction in the section should be 2P to the right. So which means that this member will be compressed and the magnitude is 2P. So 2P, then negative 4P is negative 2P. So it is compression. Then finally, in this steel section segment here, so to make the analysis simpler, let's consider the section and the left portion. So of course we have P rightward. The reaction on the section should be P rightward. So this segment will be in tension, positive P. The magnitude is P. So first, let's solve the value of P based on strength. Remember, the question is the maximum allowable value of P if the change in length is limited to 1 mm and the allowable stresses are not to be exceeded. And what is the actual total elongation of the bar? So based on strength, remember force is equal to allowable stress or working stress times cross-sectional area. So if we begin with steel, so force in steel, so the force in steel is just P. It is equal to allowable workings or allowable stress, tensile or compressive in this case. So 138, then the area is 480. It will give us 71,040 newtons. Next, for bronze, the load is 2, compressive load is 2P. So anyway, this is for both compression and tension. So for bronze, it is equal to 2P. The load is 2P and it is equated to allowable compressive stress 124 times area of bronze 645. So leaving for P, it is 39,900 newtons. Then if it is aluminum that will control, the load is 2P and it is equal to allowable or working stress 83 megapascals times area of aluminum, which is 320. So 2P equals 83 times 320, solving for P, 13,280 newtons. Then so far it is 13,280 newtons the lowest, so it's aluminum that aluminum controls in this assembly based on strength, but we have to investigate further the allowable deflection. So based on allowable deflection, because there are two segments here that are in tension, so definitely the net deflection would be elongation or elongation. 1 mm should be positive, treated as positive, because there are two segments here that are in tension. Although that's not true for other cases, but for this problem, since there are two segments that are in tension, naturally we expect that the net elongation of the system will be tension or elongation. So positive one is summation of force length over AE, and take note that the force is different for each segment, the length also, the area also, and the modulus of elasticity. So to make the unit mm, so we begin with steel. P, length is 600 mm or 0.6 meter. Let's change that to 600 mm. Then the area is 480 mm, and the modulus of elasticity 207 gigapascals is converted to 207,000 megapascals. Then for the aluminum, it is positive 2P, the force. The length is 900 mm. Then area is 320, modulus of elasticity 69,000 megapascals, so that it is consistent with the unit here in mm. Then plus for bronze, which is in compression, so negative 2P, the length is 1,200 mm divided by area 645, then modulus of elasticity is 83,000 megapascals. So from here we can solve for P in newtons, and P is 23,403 newtons. Since among these values of P, the lowest is this, so this is the maximum allowable value of P that will make the system safe. So P therefore is 30,280 newtons. Strength in aluminum controls or governs in this problem. So having found P, let's compute for the deflection. We substitute the value of P here. Then we expect that the net deflection should be less than 1 mm because the deflection does not control in this problem. So deflection actual is P 13,280 times 600 over 480 times 207,000, then plus 2 times 13,280 times 900 over 320 over quantity 320 times 69,000, then plus negative 2 times 13,280 times 1,200 over quantity 645 times 83,000. So solving for the actual deflection, it is 0.567 mm, which is less than 1 mm as expected. So that's the actual elongation based on the maximum safe value of the load P, which is 13,280. That's it. Let's proceed to problem 5. The rigid bars AB and CD are supported by pins at A and D. The vertical rods are made of aluminum and bronze. So determine the vertical displacement of the point where the force P equals 45 kilonewtons is applied. Neglect the weights of the members. So this is the given figure, so we have to analyze it well. So P is acting at the center of member CD, therefore we expect that the reaction or force in BC is half of P. And this is the deflected shape because P causes this bar to rotate about D. So call that delta P. And therefore, this is 2 times of delta P. So that's P over 2. This is 2 times delta P. And let's call this the reaction here is half of P. which is 45. So half of 45 is 22.5. Then let's transmit that. Let's consider the upper bar. This is also 22.5. Then we have reaction at A. So summation moment about A equals 0. So we can solve for the force in the aluminum rod or bar. Summation moment about A equals 0, counterclockwise positive. So force in the aluminum bar times zero point 0.6 equals 22.5 times 1.5. So that's the equation. P of aluminum bar times zero point 0.6 equals 22.5 times 1.5, or minus 22.5 times 1.5 equals 0. So the force in the aluminum bar is equal to 56.25 kilonewtons. So having found 56.25 kilonewtons, let's also draw the deflected shape. Because this is rigid, the horizontal imaginary line AB will rotate, so clockwise, like that. So we will call the deflection here of aluminum as deflection of aluminum. This is due to the downward movement because of this deflection of aluminum. So call that delta B. So take note, that's delta B, the downward movement of B due to the deflection of the aluminum. Then this 2 times delta P should be equal to delta B plus, because this bronze bar will also deflect downward, there is also a downward deformation. Then this 2 times delta P should be equal to delta B plus the downward deflection of this bronze bar here. So this is, as I said, delta B plus deflection of the bronze bar. So delta B plus deflection of the bronze bar should be equal to 2 times delta P. This is 2 times delta P because the position of the load is at the center. So by similar triangles, or obviously by experience, because it is at the center, this should be double of that deflection there. So let's compute deflection of the aluminum bar because we have found the force. So it is force in newtons, length is 900 mm divided by area 484 times 69,000 megapascal. So deflection of aluminum bar as to 0.6 equals delta B as to 1.5. So that means delta B is 2.5 of deflection of aluminum, and the deflection of aluminum is equal to 56250 newtons, 56.25 kilonewtons, or 56250 newtons times length 900 divided by area E. So 484 times 69 megapascals. So that this is in mm, then times 2.5, so 3.79 mm. Next, let's compute the elongation of the bronze bar. It is equal to 22,500. The length is 1,200 over area 160 times 83,000 megapascals. So the deflection in the bronze bar in mm would be equal to 2.033 mm. Then we add 3.79 and 2.033, then equate it to 2 times delta P. Then from there, we can compute the deflection under the load P. So delta P is equal to 2.912 mm, and that is downward in the figure. So that's it for this problem.